just a few minutes here at the beginning of this mini symposium to discuss the methods to productively collect and process data for machine learning with our Dimension line of AFMs from Bruker. Machine learning can provide new insights into our AFM data in many ways. In this symposium, we're going to talk about four, basically: characterization of features within images, classification of images, and then prediction of macroscale properties based on nanomechanical data, and then finally automated experimentation. Today you'll have a chance to hear from researchers working on all these applications of machine learning. I will be focusing on best practices for obtaining and accessing data needed to apply these machine learning methods and models to with Bruker AFMs. Firstly, AFM is not generally known as a very fast way to collect data. And machine learning typically needs a lot of data for training models. To provide the needed data volume, we need to consider two ways. One, improve the rate of acquisition, and then secondly, increase the amount of productive time that we're actually collecting the data. Here, we're looking at a tapping mode phase image or a video of images, which allows us to rapidly discriminate between crystallized polymer lamella and amorphous components of this polyhydroxybutyrate covalerate sample. The phase contrast can easily discriminate the lamella from the supercooled melt, which is much softer. And the speed of the FastScan system in tapping mode allows acquisition of an image about every 5 seconds. So this is a little sped up from real time. So in this case, we would be able to use the individual frames to teach machine learning models to identify things like the lamella or the fronts or that kind of thing. And the sample is changing, and so we don't really need to withdraw and re-engage and move to a different part of the sample as we would with many types of other experiments. Depending on the application, so there could be other bottlenecks like the engage time, the move time, finding features, and things like that. We can't always get this kind of raw speed, but luckily there is more than one way to get the data. Another way is to increase the number of productive hours available on the system. And this usually comes down to reducing the need for human interaction and increasing the automation. So methods like auto-optimization of parameters for scanning, like our scan assist function, that's one way to adapt that and make it faster. And then you could use methods like Moreau view scripting, where you can select a bunch of different co-located images or ramps within the scan area of the piezo for the AFM. This can be automated, and you can get a couple dozen images or ramps, that kind of thing. But if you want really hundreds of images like you do for a machine learning data set, then you typically don't want to depend on the user being present all the time, and so typically you want something where you can make it even more automated than that. So one thing you can do is work with, say, a large sample or multiple samples on a chuck, which can then be moved around, and then the AFM can engage on each one. And there's a couple of different ways to do that. One is using a scripted stage motion scripting method like program move, which is included with all our AFMs, or AutoMet, which is an extra cost but much more flexible. And that can be set up to drive to different locations. Also, we have nanoscript and COM interface, which allow you to run the stage and acquisition system from LabVIEW and Python, that kind of thing. So let's talk a little bit more about that. Firstly, the AutoMet. So here we have a FastScan system that is looking at a wafer full of AFM probes. One of our divisions makes AFM probes, so this is kind of an application that we're interested in. We're running this on a FastScan, and we're doing tapping mode. Basically, the system has used pattern recognition to engage on one of the die in the wafer, and it is now taking AFM images on it. It can use the AFM image to do a finer positioning, or it can move on to the next site and do another one. In this case, the system's doing about 2 measurements per minute, and this allows you to do quite a bit of flexibility. Basically, you can change things like the scan size, image parameters, and that kind of thing during the routine. You can do you can use optical or AFM based pattern recognition to fine-tune the positioning of the scanner, and then the system is going to report in real time in this pane here some results like roughness and things like that are being acquired of the data that's being acquired. Now, AutoMet is a powerful solution, and it allows acquisition of a lot of data if positions can be set up ahead of time. But for more complicated scripting like automated experimentation, an API to control the AFM is needed. So we actually have several user accessible APIs in Nanoscope. The first was Nanoscript